We began this section with the problem of reversing the process of differentiation and examine two closely related concepts, antiderivative and indefinite integral. Then, we take a first look at using indefinite integrals to solve simple differential equations where we seek to obtain explicit information about a function, given information about its derivative. In our previous work, we solved problems of the following type. Given a function f, find the derivative f prime. We now consider the reverse process. Given a function f, find a function f such that f prime equals f. In the next definition, we give f a special name. A function f is an antiderivative of function lowercase f on an integral L if capital F prime of x equals lowercase f of x for every x in L. The process of finding f, or f of x, is called antidifferentiation. To illustrate, f of x equals x squared is an antiderivative of f of x equals 2x because the derivative capital F prime of x equals 2x, which is equal to f of x. However, there are many other antiderivatives of 2x, such as x squared plus 2 or plus 3, and since we don't know how to solve for this constant, we replace it with the letter c. The next theorem restates this result in the language of antiderivatives. Let f be an antiderivative of lowercase f on interval I. If g is any antiderivative of lowercase f on I, then g of x equals f of x plus c for some constant c and every x in I. We shall use the following notation for a family of antiderivatives of the type given in the previous theorem. The notation read, the integral of lowercase f of x dx equals capital F of x plus c, some constant. This is the sign used to represent the integral, where capital F prime of x equals f of x and c is an arbitrary constant. It denotes the family of all antiderivatives of lowercase f of x on I. This symbol used is called an integral sign. We call the integral of f of x the indefinite integral of x. Here are some examples. The integral of x to the fourth dx equals 1/5 x to the fifth plus c, because the derivative of 1/5 x to the fifth plus c is, take the 5 down, you get 5/5 x to the fourth. This becomes a 0, and you just get x to the fourth. Here we can rewrite this as 1 over t cubed, and then we find that its integral is -1/2 t to the negative 2 plus c, because the derivative of that is t to the negative third. Here the integral is equal to x cubed because the derivative of x cubed is 3x squared. Now we learned in the previous section about the derivatives of cosine, sine, and other trigonometric functions. Now we just need to do it in reverse. If we can remember that the derivative of sine of u equals cosine of u du, we can see that the integral of cosine u du equals sine of u plus c. We cannot forget the c because that represents any constant that could be there, even 0. This theorem states other ways of writing integrals. First, the integral of c times f of x dx is equal to c times the integral of f of x for any non-zero constant c. It would basically be like the integral of 3x dx is equal to 3 times the integral of x. Second, we have the integral of f of x plus g of x dx equals the integral of f of x dx plus the integral of g of x dx. This can also work for subtraction, mainly the integral of f of x minus gx dx equals the integral of f of x dx minus g of x dx. Here's another example. Evaluate the integral of x squared minus 1 squared over x squared dx. First, we change the form because the degree of the numerator is greater than or equal to the degree of the denominator. denominator. We then find an antiderivative for each term, adding an arbitrary constant c after the last integration. Let's just move this to the side. And then we can find that when we factor this out, it becomes the integral of x to the fourth minus 2x squared plus 1 over x squared dx. We can then cancel, making this basically into three parts: x to the fourth over minus x to the fourth over x squared minus 2x squared over x squared plus 1 over x squared. This then becomes x squared minus 2, as those cancel, plus x to the negative second dx. Then we just integrate each part. We know that the integral of x squared is going to be x cubed, but we need to put it over 3 because when we multiply out the 3, it will need to cancel, so it is just x squared. Then we get minus 2x because the derivative of 2x is simply 2. Then we get plus x to the negative first over negative 1 plus c. We cannot forget to add the c. We can then simplify this to be 1/3 x cubed minus 2x minus 1 over x plus c. Here's another example that looks very daunting, but when we use trigonometric identities to change the integrand and apply the formula apply the formulas for trigonometric functions and derivatives we already know, we can just rewrite this as the integral of secant u tangent u. And then the integral of secant tangent is just secant u plus c, because the derivative of secant we learned in the last section is secant tangent. So it's actually much easier than it appears.